Thank you for being with us here this morning. My name is Maura. I'm the Interim Vice President for Research at Utah State University. Thank you for joining us for this winter part of our sunrise session and for following us here to this new location at the Radisson. Sunrise sessions are just one way in which we share the research and our researchers and highlight the impact that they are having in Utah. This year, for sunrise sessions and more broadly at Utah State University, we are highlighting 2020 as the Year of the Woman. It's been our pleasure to mark important milestones from Utah State University's, the state of Utah, and our nation's history, and to feature today's exceptional female researchers. We are doing this through sunrise sessions, but if you can make it up to Logan, you'll find Year of the Woman exhibits and events almost on a daily basis. And they're listed on our Year of the Woman website, which I encourage you to visit. I'd like to thank Regents for their support of sunrise sessions over the years. They are fantastic supporters of Utah State University. And their ongoing partnership with Utah State maintains our commitment to outreach and research. And of course, we get to enjoy these delicious breakfasts. At this point, I'd like to take the opportunity to recognize some of our friends from Regents who are with us today. These include Eric Hales, Vice President, and Dr. Amy Kahn, Executive Medical Director. I'd now like to welcome Dr. Kahn to the front so she can share a few brief remarks.
Great, thank you, Lisa, and good morning, everybody. It's great to see you here so bright and early at this new location. I did want to say that we're very proud to be able to sponsor this event. I really appreciate everyone being here, alumni from the university, invited guests, a number of our business partners and engaged community members. I think it's really awesome that Utah State University gets to educate our future innovators and our leaders and gets to share their best and brightest with us. This morning we'll of course hear from Dr. Hagan. I did want to also acknowledge their president, Noelle Cockett. I know she's planning to be here, I think, on the road. But really her leadership is outstanding and has been so since 2017. Also want to acknowledge Dr. Barreau, Lisa Barreau. She's a professor of chemistry and also that interim vice president of the research unit. These events don't come off as wonderful as this one without the efforts of others. And I just did want to say, folks on your team, Anna McIntyre and Teresa Seeholzer, work really hard to not only make sure that this is a lovely event, but make sure all those details keep running smoothly. So I want to acknowledge them. I also want to send greetings by way of our president of Blue Cross Blue Shield of Utah, Jim Swayze. He regrets he couldn't be here today, but sends his very best along with Miguel Rivera. Many of you know Miguel. He's been sort of steady Eddie here with this event over the last 8 years or so. The last thing I wanted to share is that it's really our privilege at Regents to not only support the employees and their families at USU, but also so many other clients and members across Utah. As we think about the sunrise session, it's important for us to embrace the dawn of a new day and a new month and a new year. And I hope that what you learn today or hear today or who you meet today at your table, you'll bring forward with you and carry that maybe to enrich your life or help you to achieve your goals for 2020. So thank you, and again, welcome. Appreciate y'all being here.
my great pleasure to introduce to you today's speaker, Dr. Maura Hagan. Maura received her bachelor's degree from Emmanuel College and her PhD from Boston College. She is now the Dean of the College of Science at Utah State University and a professor of physics. She is also a senior scientist emerita at the National Center for Atmospheric Research, or NCAR, in Boulder, Colorado. Her research interests are focused on the physics of the atmosphere and ionosphere, particularly the coupling between atmospheric regions. This includes unique space weather events, which we're going to hear more about today, and the effects of meteorological disturbances on the near geospace environment. Dr. Hagan worked as a research staff member at a little place called MIT prior to joining NCAR in 1992. She was promoted to senior NCAR scientist in 2003 and served in several NCAR leadership roles before assuming her current position at USU in 2015. Here's where I'm going to deviate from the notes a little bit. Maura has been a groundbreaker her entire career. She, through her science, has brought new insights into space weather interactions, and she's going to be able to tell us about that today. Beyond that, Maura has been a groundbreaker as a woman in science. She broke the glass ceiling at NCAR in terms of leadership. She held the interim director position at NCAR and has been a leader at Utah State University as well in promoting science and particularly diversity and women in science. I also want to say she's a fantastic leader in terms of inspiring her faculty. I'm one of them. And so she has done extraordinary work in her work as dean, and I just can't say enough about her accomplishments. Now, that's what we need to specifically talk about an accomplishment. Maura is the only member of the National Academy of Sciences at Utah State University. To be named to the National Academy means to win an award that is something recognized by your peers as being the very top of your field. Of all the scientists in the US, there are only a little over 2,000 who are recognized with this recognition. It is an honor that's bestowed on those who have made tremendous contributions to their field. Maura was cited last year, brought into the National Academy, and we couldn't be prouder at Utah State University for her recognition for all of her work. With that, I'd like to welcome Dean Maura Hagan, my former boss, my friend, to the stage. Maura?
Well, good morning, everyone. No pressure now for me to give a good talk, right? It's really my pleasure to be here and to see so many familiar faces in the audience. Thanks to my friends and colleagues for your support by coming today. And thanks to the rest of you for your interest in the sunrise sessions and I hope in space weather and in atmospheric waves, which is what I'm going to be talking about this morning. This beautiful figure kind of encapsulates in one little cartoon what I'm going to be talking about, and that is the Sun-Earth system. So, as you all know, we live in the solar system. Our star is the sun. It's where we get all of our energy. And I'm going to be talking about how the sun excites, how the sun impacts the Earth. I'll give you some introduction into the physics of the sun and its connections to the Earth, and then I'll talk about some storms that happen and how they impact the Earth, and some other exciting things. This is one of my favorite topics, so I'll try not to get too carried away as we go. So I'm going to start off by talking about the magnetic sun. When you think about the sun and you look at it in the sky, you think about that heat, that source of light, that source of heat. But underneath that all is a magnetized body. And you can see that in this picture taken from the Solar Dynamics Observatory spacecraft. So if you look at the sun in the visible, which is what we do, we see the photosphere, the outer layer of the sun. But if you look at different wavelengths, you can see below that surface, and that's what you're seeing here. And you can see the features of the magnetic sun, which include the polar regions, which are just basically like holes where the magnetic field can emerge, both from the south and the north pole. But you can see a lot of structure in other regions of the sun, light spots and dark spots. And if you look closely at those light spots, you can see they look like ropes or loops. And in fact, I'm helping you to see those loops with this cartoon that Wyatt Trauber helped to generate. Thank you to Wyatt and to Anna McIntyre for helping me with this presentation. These loops are going to be very important to the rest of my story as it proceeds. Now looking at the photosphere again, looking at the outer layer, you can see these dark spots. Has anybody heard of sunspots before? See some people nodding, yes. So sunspots have been observed since the 1800s from the ground by telescopes and so forth. And you can see that record here. In the top panel, you're looking at sunspots as a function of latitude of the sun from pole to pole, and as a function of time from 1870, and actually this sequence ends in 2016. And you'll notice that there's this quasi-11-year pattern to the sunspots. And they start off at the highest regions, high latitudes of the sun, and then as the sunspot cycle progresses, they move towards the equator. In the bottom panel, the surface area of those sunspots is added up together. And so you can see the solar cycle, the rising and the falling of the solar cycle from that period of 1870 through 2016. And I'd like you to notice that there's a lot of variability from cycle to cycle. You have times when there aren't so many sunspots, like in the late 1800s, as well as in the 2010s and right now. The sun is actually in a very quiet period. But if you look back into the 1950s and 60s, and again in the 80s and 90s, you can see that the solar cycle was much more active. That means that there's chances for more solar storms to occur, for more extreme events to occur. Whoops. So there's something on the screen that says, just one more thing. Perhaps I've forgotten just one more thing. Okay. Leave it to Anna to take care of it. All right. So in addition to those sunspots, and in addition to those loops, that magnetic sun, there's a constant barrage of particles that are being emitted from the sun in 3 dimensions called the solar wind. And I hope you can see that in this animation here, that solar wind is variable. It's not a constant thing, but just like the winds that we experience on the ground, we have gusts, right? Okay, I'm having a technical difficulty. Oh, no, here we go. So now I'd like to pause for a minute and talk about the Earth. Does anybody in this room ever do an experiment in high school where you had a bar magnet with filings, iron filings, and you had to kind of try to determine what the equipotential magnetic field lines were? I see people nodding their heads. So if you were successful in that experiment, you were able to conjure up a picture with those iron filings that looked something like this, right? Where you had the north and south pole of that magnetic bar, and the equipotential loops, the magnetic field lines circling from pole to pole. Well, actually, to first order, the Earth is like a dipole. It's like a magnetic dipole. So when the solar wind, which is coming constantly from the sun, impinges upon that magnetic dipole, it compresses the sun side of that, those equipotential field lines, and the tail of the magnetosphere is elongated. So we call this structure, this magnetic structure around the Earth, the magnetosphere. And it actually protects us from this solar wind. So if you go to Mars, for example, where there's only a remnant magnetic field, the magnetic field is very weak and only occurs in certain places on the planet, the solar wind is impinging right onto the surface of the planet, which makes it a much more hostile environment for life, for example. So, with that background, I'm now going to talk about some solar storms. So when the sun becomes angry and erupts, there are extreme events that can affect the Earth if the extreme events are lined up appropriately such that we can encounter them. And that's what is going to be illustrated here. So in this animation, which is also taken from a spacecraft, you're looking at the outer solar atmosphere, the corona. So this is the atmosphere above the photosphere, which is what we see. And the photosphere is so bright that when you look at it through a telescope, be it from the ground or for Earth, you have to block off the photosphere with something called an occulting disk so that you can see the weak signal, the weak light emanating from the corona. And now if you look here at about 10 or 11 o'clock, you can see an eruption occurring from the surface of the sun. This is called a coronal mass ejection, a CME, as we say for short. And that eruption, you can see, looks like one of those loops that's lifting off from the surface. And in fact, that's what's happening. So that is a magnetic cloud. It's a cloud full of magnetized particles. That's one type of solar storm, a coronal mass ejection. You can see those coming when you're looking at them. It takes about 2 or 3 days for a CME to reach Earth orbit. The other event that's important to know about is what's called a solar flare. These are much smaller events. They're much shorter duration events. They occur in places, in these bright-looking places which are called loops on the surface of the sun, also magnetic phenomena. And in this animation that you're looking at, all that fuzziness is the particles being sensed or seen by the spacecraft. So it's hitting the spacecraft sensor, and that's can be disruptive. In this case, it allows me to tell you what the particles are doing. So when a CME, and by the way, a flare, it travels at the speed of light, so they're much more hard to predict, to see them coming. Some people can estimate that you might have an eruption, but other than that, it's a subject of ongoing research to try to understand and predict these things. All of this stuff is, actually. So in this animation, what you're seeing is what happens when that CME, when that magnetic cloud actually is lined up and is geoaffective, so it affects the Earth. You can see the cloud, it hits that bow of the magnetosphere, there's reconnection, those magnetic field lines are drawn back over to the tail, so the magnetic field is compressed on the sun side, and then on the back side it's also compressed, and reconnection, and all of those particles are impinging upon the atmosphere of the Earth and causing beautiful aurora. aurora are one of the beautiful impacts of the Sun-Earth connection and of a CME affecting the Earth. But there are other impacts that aren't so nice. And I'm going to speak to them from this figure here. So you're going to have particles from CMEs and particles from flares. Sometimes they occur together, sometimes not. They don't have to. A CME can happen without a flare and vice versa. But the issues are they can damage spacecraft. You saw the effects of that fuzziness on the sensor that I showed you a few minutes ago. They also can disrupt GPS communication. So you can imagine now, I showed you that solar cycle sequence. We're in a period where the sun is not very active. But if the reverse was true, we could expect a lot of interruptions in our GPS. And you know we use GPS for everything, including getting to the Radisson this morning for some of us, right? But also it's used in agriculture, ATMs, avionics, in operation of aircraft, in astronaut safety. So when the International Space Station is inside the magnetosphere of the Earth, they're protected from the particles and the radiation coming from extreme events from the sun. But when that magnetosphere contracts during an extreme solar storm, that's not true. And so they're subject to those effects. I mentioned avionics. There are currents that are driven in power system grids, as well as in cables, in submarine cables, and in pipelines. And those currents in pipelines corrode the pipelines, cause a lot of damage there. But in the power system grid, they can actually cause outages. And in 1989, in Quebec, Canada, one such outage occurred. It's illustrated with this animation. That outage lasted 9 hours in order to bring the power back up. And you remember 1980s and 1990s were the two periods where we had a really active sun in the recent past. We don't have to worry too much about being devastated by coronal mass ejection or another extreme weather event from the sun, because we have something called the Space Weather Prediction Center, which is operated by the National Weather Service and as part of NOAA, and they monitor the sun at all times. You can see figures that are reminiscent of some of the figures that I showed you in describing the physics of the Sun-Earth connection. And they can, and they do, broadcast warnings to all of their customers. And the customer base is growing exponentially year after year because of our reliance on the space and communications. Okay, so I've been talking about the magnetic sun and how that affects space weather. I'm now going to talk about the radiative sun for a couple of minutes, and that's the sun we're most familiar with, the source of heat and light. And that comes in all directions, 3D, just like the solar wind. But I'm mostly interested in talking about the light that is emitted from the sun and the spectrum of light that encounters the Earth's atmosphere and actually structures the Earth's atmosphere. So the infrared and visible light from the sun is absorbed in the troposphere and by the Earth's surface, and that's what keeps us warm, right? The stratosphere, which is the layer above that, is where we have our ozone layer. Everybody's heard of the ozone layer, I assume. Nodding heads, right? And that layer absorbs ultraviolet radiation. It protects life on Earth by absorbing that ultraviolet radiation. What many people probably don't know is that in the outermost layer of the atmosphere, the so-called thermosphere, the far ultraviolet light and extreme ultraviolet light, so the shorter wavelength parts of the spectrum, are absorbed up there. And this part of the atmosphere is extremely hot compared to the other parts of the atmosphere. This part of the atmosphere is also where our satellites are orbiting. It's where our station is orbiting, space station. It's the other thing that the ultraviolet, the FUV and the EUV do is they ionize the atmosphere. So this is where we have the so-called ionosphere, which is the vehicle for communications, the electrically charged part of the atmosphere. This part down here is, for the most part, neutral. So, the other thing that happens when that solar radiation is absorbed in those layers is that it excites waves that we call migrating solar tides. And I'm going to speak for a minute about how those tides are excited. So if you imagine you're sitting on Earth here, rotating around the sun, you can think about the sun turning on at sunrise and turning off at sunset. So you can imagine that there's also a heating function that is associated with that square wave, that heating going on and going off. Well, for those of you who know what a Fourier decomposition is, you will understand that you can break that square wave up into components, which consist of a mean, and then a 24-hour variation, and a 12-hour variation. Those of you who don't know about Fourier decomposition can just believe me. That's the truth. And so for the rest of this talk, I'm only going to speak about the diurnal variation, which is the 12-hour variation, which is the most important heating part of the spectrum. So if I know what that heating function looks like, and I know how it's being absorbed by ozone, or how it's being absorbed in the troposphere by water vapor, I can come up with a scheme and plug that scheme into a series of equations. I'm a numerical modeler, so I solve equations, momentum, energy, continuity, etc. And I can predict what the tides, the solar atmospheric tides will be. Now, you're sitting there thinking, tides? She's talking about tides. She's talking about the tides being heated by the sun. The tide I know about is the ocean tide. And that's different, but it's not so different, actually. The ocean and the atmosphere are both fluids, and they obey the same laws of energy and momentum, etc. What's different is the forcing function. So the ocean tide is forced by the gravitational pull of the moon. And we do have ocean tides in the atmosphere, but they're very small compared to these solar tides, these thermally driven tides. So that's why I'm focusing on it. But in the same way, we like to be able to predict when the low tide is going to be, so we can walk the beach without having to climb over a jetty. In the atmosphere, we want to be able to predict what the tides are going to do for lots of reasons. For me, it's intellectually stimulating, but there are actually practical reasons as well, which I'll talk about. So I began my career predicting what the tides would look like from the ground all the way up through the lower part of the thermosphere. And then, after a while, I got to thinking about what a different source of tides might be. And this source would be also attributable to the sun, but indirectly. So perhaps if you've been to the tropics, you're aware that there's this pattern of deep convective clouds called the intertropical convergence zone, which moves back and forth across the equator with season. These clouds are persistent, they're ubiquitous in that tropical region, and so kind of like that solar radiative source that's always there, it's suggested to me and to my colleagues that perhaps they would be a source of tides also. The fact that they're really deep counts, because you have to have a heating source that's not thin, like the clouds that we see when we look up in the sky. But if you've been to the tropics, you know what I mean about those deep towers. So the thing that makes them, it turns out that it is a good source of tides. But what makes them different from the radiative source is they don't move with the apparent motion of the sun. So you can imagine that heating source, it's either on or it's off. But in the case of these towers, there's longitudinal variability, and they don't move with the apparent motion of the sun. So we also parameterized or came up with a scheme to put this kind of heating function in our model, in our equations, and solved, and came up with predictions for what these tides would be doing. Okay, one more thing, and then I'm going to show you an animation of what the results look like. So the interesting thing about tides, especially those that are excited in the troposphere and the stratosphere, is that they're not important at those regions where they're excited. They're small. But the atmosphere of the Earth, or any atmosphere, decreases in density with altitude. So if the tide is propagating upward, it's moving upward, the amplitude of the wave is growing, so that the wave that's small in the lower part of the atmosphere becomes really big in the upper atmosphere. And in fact, it governs the dynamics of the region. And you're going to see in this animation, this is the result of the model calculation for the diurnal tide, the migrating component. So this is the east-west wind, and these contours go up to 20 meters per second. So from peak to trough of the wave, that's 40 meters per second. That's big, and that's measurable. Just focus on the upper panel for a minute, and you can see no matter where you are in longitude, if you're just sitting there, you're going to see the same thing in the American sector that you're going to see in the Asian sector, Indian sector, no matter where you are. It looks the same. And in fact, the peak and the trough are moving with this apparent motion of the sun. So it's really the peak that's moving with the apparent motion of the sun. So this is why it's called migrating, because it migrates with the apparent motion of the sun. On the bottom panel, wow, it looks so different, doesn't it? So if you're sitting in the American sector, you're seeing something very different than you are in the African sector or the Asian sector. This is not moving with the apparent motion of the sun. But if you pick just one spot, you would see, just like you did up here, one peak and one trough. So it's a diurnal tide. This is a signature of the non-migrating tide. And if you squint, you will see that there's about 3 peaks and 3 troughs. 3 light colors, 3 dark colors. And this was a prediction that was made in 2002 and 2003 with my colleague Jeff Forbes. Lots of people didn't know what to make of that, but one of I'm going to stop for a minute. You saw this figure earlier, and we talked about all of the results of extreme events. But atmospheric drag on satellites is really important to orbital prediction. And if you don't know, and you don't account for the migrating waves or the non-migrating waves, you're not going to be able to predict the density of the atmosphere correctly, and so your orbital predictions will be off. So that's why it's important to other people who don't just find this fascinating. Okay, my other colleague, Thomas Immel, who was analyzing emission brightness, this is the figure of the raw data over here on the left, from the so-called image satellite, the FUV instrument, noticed this pattern over the equator and called me up and said, do you think that this could be attributable to non-migrating tides? And so he's making measurements now in the ionosphere. So this is much higher than my predictions, which I showed you were at the gateway to space, just at the border between the mesosphere and the thermosphere ionosphere. And we thought, yeah, perhaps it is. And so what you're seeing on this figure here is an extension of the observations, and superposed underneath it are contours of the model predictions that I showed you a few moments ago. Then we did a numerical experiment with my colleagues at NCAR, and I don't have an ionosphere in the simple model that I use. So my colleague Ray Rogel, who has a general circulation model of the whole ionosphere thermosphere, would say, well, let's just put your tides down at the bottom of the model, and we'll shake that model like we would shake a rug and see what happens to those waves as they propagate up. And so that's what we did with this simulation. And what you're looking at here is electron density. So this is a measure of the ionosphere, and it's a snapshot of what the Earth, the ionosphere density looks like at 20 universal times. So here's the day side, you have lots of density, and at night you have a lot of recombination because the sun is turned off. But if you're observing the ionosphere from a satellite, you can't see that picture. You can't see all the local times. You know that the Earth is spherical. I've unwrapped the spherical Earth here to illustrate density as a function of latitude and longitude. What the semi-sun synchronous orbit satellite does is it makes a measurement at the same local time throughout the course of a day. So it builds up what we call an asynoptic pattern. And so at Greenwich, it's 20 UT is the same as 20 local time. But if I move that and construct what would the satellite see at 20 local solar time, I would get a picture like this in the bottom. And you'll notice that there's this wavy structure here, a quasi 3 to 4 wave pattern that is associated with the non-migrating tides. So this was proof that what Thomas observed from the image FUV and the density was actually attributable to the non-migrating tides. We did a lot of things to show that other potential sources were not involved. So then people started looking at their data, and they found wave 4 everywhere. Everywhere they looked, they found this signature of non-migrating tides. This didn't happen until the recent past, the past 10, 12 years. But this was a very exciting discovery. And in fact, earlier this year, we had the launch of a satellite called the Ionospheric Connection Explorer, ICON. And ICON's mission is to try to further study these non-migrating tides. So there was something good about that prediction that we did nearly 20 years ago. Okay, so I told you a very simple story today about one wave, one set of waves coming from the lower atmosphere to the upper atmosphere and its impacts on space weather. This is a simulation done by my colleague Hagan Yu from NCAR, and what you see in this simulation is that there's a myriad of waves that are coming up. So this is an animation of what the surface of the atmosphere would look like if you could see it with the naked eye. We can see the surface of a pond or the surface of the ocean. This would be what the surface of the atmosphere would look like. And so you can see that the tides, those global waves, are there, but superposed on that is lots of smaller scale waves, regional scale waves, waves that are excited by thunderstorms, waves that are excited by all kinds of interesting phenomena in the lower atmosphere. And so there is a new satellite, that a new mission, an instrument that's being developed to fly on the space station, the International Space Station. And the principal investigator of that mission is Mike Taylor, Professor Mike Taylor of the physics department at Utah State University. And the instrument is being built at the Space Dynamics Laboratory of Utah State University. This is a very exciting mission. It's about $45 million, and if all goes well, it'll launch in 2022. So I will conclude by saying I hope that you will have the opportunity to hear from Mike Taylor in a couple of years at one of these events, and he can tell you more about space weather and the impacts of waves from the lower atmosphere on the upper atmosphere. So I want to thank you all for your attention. I want to thank Regents, thank my colleagues at Utah State for their assistance and for the invitation to speak to you all, and thanks to the audience. I'm told we might have questions, or time for questions.
Yes.
Is somebody going to moderate, or do you want me to?
I'll moderate.
Okay.
Yes, question.
I have heard, and I don't know if it's science fiction or true, about the Earth as a body has a certain cycle of magnetic reversal. What is kind of the arc length of these cycles? Are we going into one, and what does this do to everything?
Yeah. Well, I don't know the answer. So the question, if I heard it correctly, is about the cycle of the magnetic pole of the Earth flipping. And I believe that you are correct. However, I don't know what the timescale is for that to occur. I do know that on the sun, it occurs every 22 years. So the polarity of the north and south pole switch, and it happens within the interior is something called a solar dynamo that drives that magnetic reversal. But that's the extent that I can talk about it. I'm not a solar physicist.
Yes.
All of this information, does it help create what weather we have here? Like when we listen to a weather broadcast and they're talking about the storms that are coming in, does the sun and all that influence what's happening there?
Good question. Well, definitely the sun influences it because that's the source of heat, that's the source of energy. But in terms of the downward penetration of space weather events, of the coronal mass ejection or the solar flare events, no, it doesn't penetrate that deep. There is evidence that it penetrates as deep as the stratosphere during extreme conditions. You can actually have a depletion in the ozone layer at high northern latitudes, but it quickly recovers after an extreme event. So, yes.
Does the electron density being higher during the day, is that what makes radio waves not travel as far? Like, when I lived in Southern California, I could get KSL because it's Clear Channel. Down in Southern California at night, certainly not during the day.
So you're absolutely right that you need to have ionospheric density in order to have the waves propagate. That's the medium through which they propagate. So the problem that I was speaking about with the communication issue is that there's a patchiness that can occur when we have a disruption in the ionosphere due to some kind of extreme solar storm. And so that interrupts communications because, you know, if you want to think about it as holes in the ionosphere through which the radio waves can't propagate, or any other kind of wave. There's also maybe enhancements, or there's some kind of chirp that happens in the ionosphere from a different source that interferes with the communication as well. Call it scintillation.
I have a question for you.
There's two more.
Is there two? I didn't see a hand.
Sorry,
There a
hand
hand?
here?
Yes.
So you talked about this 11-year cycle of sun activity, and you seem to tie that to the aurora borealis. So is there when's the next best time to go see the northern lights?
Good question. So you don't have to have an extreme event to see the northern lights, but of course they become much more dynamic, and actually the auroral oval, which occurs at about 60 degrees north, expands during an extreme event, and we can see it here at mid-latitudes. There's been sightings of aurora over Cuba, for example, during an extreme event. For reasons that are kind of difficult to explain to you, the aurora are more intense during equinox than they are during solstice. So spring and fall versus, and it's something that has to do with the alignment of the magnetic field that allows the particles. So you remember those equipotential lines, right? There's actually a source where particles can come in. It's called the cusp, where those lines, those equipotential lines meet. So that cusp is tilted in the sunward direction more in equinox because of the offset between the magnetic pole and the geographic pole. Maybe more information than you wanted, but yeah. But of course it has to be dark to see the aurora. So I don't recommend going to see it in the summer. You'll be disappointed.
Doug.
Dr. Hagan, I wonder if you could just give us a little autobiographical sketch for a moment. How did you become interested in science, and in particular space weather? And then the follow-on to that is, what advice do you have for us to encourage our daughters and granddaughters to become interested this way?
Wow, thank you, Doug. Well, I was good at math. I loved math, and I was good at math. And I went to college with full intentions to be a math major. And then I thought math got kind of boring after a while. And my academic advisor said to me, you should take a physics course. You would like physics because it involves a lot of math, but it's applied. Physics? I hate physics because I had a physics teacher in high school who was all about the notebook. And the notebook had to be like this, and the notebook had to be like that. And it didn't intellectually stimulate me, shall I say. But Dr. O'Brien convinced me, and I took a physics course, and the rest was history. I fell in love with it. I knew I did not want to be a teacher, a high school teacher, so I needed to go to graduate school, I felt. But I was not driven by space physics at that point. However, at Boston College, there was something called Space Data Analysis Lab that was affiliated with the Air Force Cambridge Research Lab. And they were doing a lot of space physics. So the Air Force is the conduit for a lot of space physics to this day. And so I became exposed to space physics. Well, rewind back to the Apollo program. I was riveted by the Apollo program and watching Neil Armstrong land on the moon and people bouncing around the lunar surface. And I just was fascinated by it. So I think it was that synergy between that experience, that exposure that I had as a kid that I was fascinated by, and then the opportunity to work in the area of space physics that then led me to do my degree. And I started studying tides when I was at, I actually did my research at MIT, even though my degree is from Boston College. I was working at a radar facility in Millstone Hill, Massachusetts, and looking at the backscattered signals from the ionosphere and seeing these pronounced variations that were harmonics of a solar day that were signatures of tides. And so it wasn't until I went to NCAR that I started doing numerical modeling. But yeah, that's it.
And the second part of the
Oh,
question?
the second part, thank you. What would I tell? I would encourage all children to explore everything that they're interested in. And not to be afraid to do something different, even if your friends don't, you know, I mean, I was the only woman in my circle of friends in college that was a physics major, but it was okay. So, yeah, that's what I would be saying.
President Hagan.
Well, first, as you can imagine, this was a pretty complicated concept to understand. And then think about coming in about halfway in and try to understand it. So if you've already answered this, that's fine. So I'm thinking that while the sun and the moon have effects on the Earth, I guess my first question is, does the Earth have effects on the sun and the moon? And if so, I'm bringing up the words climate change. And as we're possibly causing climate change, would all these patterns then become less predictable? Or there are others who say climate change is more predictable. It's just one of those waves over time that's occurring. Could this kind of study be used to detect whether or not climate change is caused by humans or is more of a predictable thing?
So, thank you for that question, and I didn't address issues of climate change in the near space environment or the upper atmosphere. The whole topic is complicated because there are so many influences. Coming back to the first part of your comment, the Earth absolutely affects the moon. Absolutely. The moon is the satellite of the Earth. The Earth really doesn't affect the sun. The sun affects the Earth. But the Earth does interact with the other planets, etc. In terms of solar drivers of long-term change in the tropospheric climate, yes, the sun does have an effect. It is minuscule compared to the effects that the anthropogenic effects. So absolutely, there's unequivocal evidence that our use of fossil fuels is impacting the atmosphere. It's hard to deconvolve it given the complexity of what goes on in the atmosphere. It's actually easier to deconvolve it in space than it is in the thermosphere and ionosphere, and I have a slew of colleagues who have worked on that. The challenge is the record of observations. So the satellite era began in the 1950s, right? So that's as far back as you can go. But you can see, absolutely, you can see trends in density. So interestingly enough, carbon dioxide in the lower part of the atmosphere heats the atmosphere. You all have heard about the greenhouse effect, right? In the upper atmosphere, carbon dioxide cools the atmosphere because it radiates to space. It radiates energy to space. So what is happening in the thermosphere is that that layer is contracting because it's cooling. And so you can measure, if you look at density at a particular altitude from satellite records over since the 1950s, you can see that contraction unequivocally. So yes, climate change is happening. Some people call it the miner's canary in the upper atmosphere. You can see it in other things. Noctilucent clouds, for example, these are clouds that happen high in the atmosphere. Their occurrence is happening more in a broader range of locations, not only in the polar regions, but now encroaching on middle latitudes because of the cooling. They're formed by ice crystals, so you can see that happening. It's behind you.
If I heard you correctly, the prediction of these atmospheric tides occurred like in the early 2000s. So what did the people putting up satellites do prior to that? Did they just kind of put on a helmet and go?
So perhaps they did put on helmets, I'm not sure. But you know, there's always some uncertainty associated with orbital prediction. And in fact, you know, during a big solar storm, during an extreme event, like what we would call a hurricane or a tornado on Earth, the people who track satellites lose them, and then they have to find them again, you know. So, you know, the satellite tracking people in the Air Force, they pretty much help. But the problem is becoming more challenging as we have more and more spacecraft, and we have all these commercial entities that are providing internet service all over the world. The Starlight effort by SpaceX being one example. So you have to worry about collisions and orbital debris and so forth. So the problem is more acute now, I would say. The other thing that I think is worth considering is we would not have discovered this if the sun was really active. It's hard to see the effects, the meteorological drivers of space weather when you're having a really active sun that's constantly barraging the Earth with coronal mass ejections and so forth. So I was kind of lucky, maybe, that we were able, that our predictions were confirmed. Thank you for that question. Yes.
What are the particles made of that are coming from a CME?
I'm sorry, could you speak up?
What are the particles made of?
The particles are protons, electrons, alpha particles, which are helium-charged atoms, primarily. There are others, but those are the major constituents. So they're pretty simple, but they're highly energetic. Not the same energy ranges that we observe in the ionosphere of the Earth's atmosphere, for example. Yes, MEV.
I just want to comment on Doug's question, because I think the more we introduce our children, our grandchildren, our daughters, our granddaughters to scientists like you, so they can see a woman role model in a non-traditional position, and that it's possible for them too. So I just wanted to comment.
Thank you very much. It's an important, I take it as an important responsibility to try to let people know that you can look like me, you can be a mother, you can be a grandmother, a sister, daughter, aunt, etc., and be a scientist. Yeah. Yes.
So you mentioned Cuba earlier. I'm actually going to Cuba in a couple of weeks.
Oh, good.
I think I'll see the northern lights. The aurora volume. Do you think I'll see an aurora?
You probably will not see any aurora in Cuba in the next coming weeks. We are actually in the rising portion of solar cycle 25. The chart that I showed you cut off at 2016, but we've now are coming into a new solar cycle. But it's not predicted to be strong.
So I Googled it, and so it's, like a long time ago that it happened?
Right, right. So,
1800s?
well, yes, there are lots of events that people cite. So I don't know which one you Googled, but yes, the event where Aurora was seen in Cuba was not in my lifetime. But in my lifetime, there's been sightings of Aurora in Texas.
I was just curious too, just looking at the picture there. So I'm not very familiar with the sun's properties, but eventually it will burn out.
The sun?
It's like a barbecue grill, right?
Yeah, it does look like a barbecue grill. Well, yes, the stars do have a lifetime, and our sun, it will eventually die. You know, if the stellar theories are correct, it won't be in our lifetimes. I'm sorry I can't say more about that. I mean, I've told you about all the solar physics I know. I'm not a solar physicist, so, but maybe somebody else in the audience is.
No, I just thought that maybe the sun beams, you mentioned about sun beams.
Yes, yes.
I imagine that those are intended to cool off the sun so it won't burn out.
Okay.
And then talking about students' exposure to science, math, and all that. At the Salt Lake Community College, we usually have, during summertime, a special class for students to be exposed to all these.
Wonderful.
Yeah, for them to be encouraged to pursue things like you are doing.
Great. I'm glad to hear that.
I don't think it's only at the Salt Lake Community College.
Wonderful.
I've taught for 24 years, but
Yes.
I think several other colleges, universities.
Yes. I think people do take it seriously, and there's many efforts to try to entrain students to think about careers in as we say, STEM, science, technology, engineering, and mathematics, but in any career, you know.
Yes.
Paul.
So you may have touched on this earlier, but in your mind, if you could just bring out one or two points where space weather and Earth weather interact.
So from my point of view, I think it's really the meteorological weather that's impacting the space weather. So it's really you can think about a big, huge storm. Like you see those tropical cyclones, how massive they are in size. They act like a moving mountain in the lower atmosphere. And so waves are generated and are propagating upward, and you saw that in that last animation. So that's a foundational connection between a weather system that is excited on Earth. The energy from that system originates in the sun. The non-migrating tidal source is associated with latent heat release associated with raindrop formation. So latent heat of evaporation. That evaporation occurs because of the solar system. So it's all connected, in my opinion. Yes?
So if I read in Farmer's Almanac that because of this solar cycle, here's the weather forecast for 6 months from now, you look at that and say, no, there's really nothing.
I don't understand that conjecture. That's what I would say. I don't doubt that there might be some statistical relationship or something, but I don't see a physical driver. Okay?
Yeah.
I think we're going to bring this to a close, but Dean Hagan, I would like to ask you one thing.
Oh, okay.
When we're talking to students and getting them excited about science, one of the things that I've seen is they're very interested in solving the problems that are going to be the problems they encounter throughout their lifetime. So as you think about your field, what is the problem that you could point to get a student excited about?
Oh, jeez.
I mean, one of the things I was thinking about is the dependence of our whole life now on satellite technology. And so I think it's a very relatable area for students because
Right.
of everything they will have as their technological
Sure.
devices in the future.
Sure. Well, I'm going to quote my friend Nikki Fox, who is the director of the Heliophysics Division and the Science Mission Director at NASA headquarters. And Nikki would say, it's a great time to be a heliophysicist, which means it's a great time to be a solar and space physicist. And I think it's because of all of these opportunities. We now have something called Parker Solar Probe, which is really going to touch the solar atmosphere. She would say it was going to kiss the sun. And so there's all kinds of discovery science that's yet to be made in the Sun-Earth system that we study. And the applications that you're referring to are entirely relevant. So unraveling the puzzle that is yet to be understood, I think is, as I said earlier, intellectually stimulating, but with a practical application. Thank you very much.
With that, let's thank Maura for a wonderful talk.
So I'm Noel Pocket, president of Utah State. I regret that I was caught in traffic. If only we had the kind of predictability of traffic that we do with these atmospheric waves and tides, I would have been on time. I know that Lisa Barreau, our Vice President for Research, mentioned that this is Year of the Woman at Utah State University. This is exactly the kind of thing that we are highlighting, that women are in leadership roles, they're in research roles, they're in creative art roles, and we want our state, our country to know that and to see that there's pathways for young women to follow us. I also was reflecting that it wasn't a deliberate thing, but if you look back at this program, all of us on that program are women. We have Dr. Khan, who's the executive physician for Regents. We have Lisa Barreau, Vice President for Research. We have our speaker, Maura Hagan. The other interesting thing is that women multitask, right? We have Lisa, that's Vice President for Research. She was recently named to her society, American Chemistry Society, as a fellow. And then Maura Hagan not only does this research, named to the National Academy of Science, but is our Dean of Science. So I'm just so proud of our women at Utah State University, past, current, and future. And I hope that, again, you connect with us through Year of the Woman and continue to support our Sunrise session. So thank you so much for coming.
I hope Allison's okay.